Hello and welcome to another day at class. Today we're going to start with order of operations, and then we're going to start talking about prime and composite numbers. We're going to talk about factors, prime factorization, and some divisibility rules. So all of this hopefully is a review from some stuff that you had in high school or college. Like I said, any of these things that you really hang you up, feel free to talk to me about, so that way we can get those knocked out and you can move on with learning more math. So order of operations, one of the most common acronyms that you see in mathematics is please excuse my dear Aunt Sally. I don't know what Aunt Sally did, but you should probably excuse her. And this is the most common one used to help students remember the order of operations. So each one of these letters that in this sentence, the starting letter for each word, represents one for what we should be doing, working an equation so that everybody gets the same answer. So we start with parentheses. Anything inside of parentheses, we work those out first. Then we move to exponents. And then we do multiplication or division. And that's key. It could be either one. Just because multiplication is listed first doesn't mean you do multiplication before division from left to right. And then we do addition or subtraction from left to right. Once again, we do addition or subtraction last, but it doesn't mean that subtraction must be done after addition, all addition, and the problem's done. And I'll show you some examples of that. So we just move left or right, and whichever one we come up with first, or come to first, that's the operation we do for those. So let's look at some examples here. We'll start on the left side and work out each expression and simplify these. So the first one, we've got 3 plus 3 times 4. Remember, sometimes we use these dots for multiplication. Sometimes we just wrap them in parentheses to mean 3 times 4 here. So there are parentheses here, but the parentheses has no operations going on inside of it. So it's just there to show it's not 34, it's 3 times 4. So no parentheses to work out, no exponents. Remember, exponents are when you've got a number raised to a power. There is multiplication and no division. So moving left to right, the first thing we come across multiplication-wise is 3 times 4. So we go ahead and do that, and we get 12. And then now the last thing is just to add. So 3 plus 12 is 15. So this expression simplifies to 15. Now, notice if somebody was just working the problem left to right, and they weren't paying attention to the order of operations, they would get this problem wrong if they add it first, and they would also get a different answer. So 3 plus 3 is 6, and then if you times it by 4, you would get 24. So because we get two different answers depending on the order that we do things, that's why we have rules for how we should approach a problem and what order we do things. Otherwise, two different people would be getting two different answers here. So we do the multiplication first, and then we add. So going on to the next one, we're going to start, and notice we've got 5 times something here, but don't just jump right to multiplication. We want to do the parentheses first. So we do have parentheses with an operation going on inside. So we're going to say 3 plus 2 first, and then times it by 5. Now we can say 5 times 5 is 25, and that's our answer there. I want you to look at this next one. Pause the video and give it a try. All right, I'm assuming you give it your best attempt there. There are no parentheses here. There are no exponents to worry about. Looking at this, we've got multiplication and division going on. Now, this is probably the rule that most of my students usually mess up on, if they are going to mess up on this stuff at all. And that's just because the word multiplication comes first. They think you've got to multiply first. It's multiply or divide, left or right. So moving left or right, the first thing I come across is 12 divided by 6. So division comes before multiplication here as we move left or right. So I'm going to say 12 divided by 6 is 2, and then 2 times 3 is 6. So our answer is 6. And you say, would it make a difference if I multiplied first? Well, if you multiplied, you'd have gotten 18, and then 12 divided by 18 is going to be a rational number here. Let's see, divide both by 6, we get 2 over 3, or 2/3. So totally different answer because we used a different order. We don't want to go that route. Follow the order of operations there. All right, so the last one, once again, you can pause the video if you'd like. Give it a try. And working this, we're going to first start with parentheses. There are no parentheses. There are exponents, though. We've got 4 raised to the power of 2. So I end up with 7 plus 2 times 16. And then going left or right, I've got multiplication in here, so I end up with 32 plus 7. And 32 plus 7 is 39. So 39 is the answer for that one. All right. So we're going to move along now. That's the order of operations. Like I said, if I was teaching it to you for the first time, like if it were a high school course, we'd spend a good whole lesson on it, maybe 2 days on it, depending on the audience that I was speaking to. But I feel comfortable that most of my students remember that from high school. Once again, though, if you struggle with it, if you're getting those wrong, or if you get a lot wrong with the homework, make sure you meet with me at some point and we can work through that. So I've got in your resources this week's hundredths chart for you to go through. I think the hundredths chart is an excellent tool for teaching elementary school math. And this is not a methods course where I would take you through some great videos showing some teachers that were working with students by adding 10s or adding 20s. Like if you're adding 10 to 33, it's just a drop down and they can see that. Or if you're adding 22 to it, you can drop down twice and that's 20, and then move over twice and you're right here at 55, and 33 plus 22 is 55. A lot of other great things you can do with it. Today we're going to talk about multiples. So what I want you to do, and really I've got all these multiples filled out for you, so let me just tell you what I normally do in my classroom. So if I was teaching this to you at Randolph and we were going through these in the classroom, I'd hand you a bunch of these little charts, and I'd either give you some coins, or I would just, sometimes I put them in plastic sleeves and let students use expo markers to mark them out, or some students just color them in. And I would say start off by coloring in 2 and fill out every multiple of 2. So you have 2, 4, 6, 8, 10, and so forth. And so as you do this, this is what you get, shading multiples of 2. Let me move this up so you can see it. It's cut off right there. So there it is, and you can kind of start seeing patterns here. So this is another cool thing. If you're teaching a young group of students, they can start to see patterns visually here with multiples of 2, and you can talk about that with them. They also make these charts, by the way. You can make them large displays for your classroom, and they have like plastic sleeves where you can put transparencies in there to shade it in front of everyone. Of course, the computer nowadays always works for this too. But here it is, multiples of 2. Then go back to a blank one and shade in multiples of 3. So that's what you get when you get multiples of 3. So you can talk about patterns there as well. We're going to keep this going all the way through multiples of 10. So this is a little bit less contrast here, but this is shaded multiples of 4 there. And if you look in the resource files, these are actually colored files, so you can see them a little bit better. I should have copied over the colored version. Here's multiples of 5 shaded, multiples of 6, multiples of 7, patterns a little less organized there, multiples of 8, multiples of 9, and then last here, multiples of 10. If you want to look at those, they're in the resources. You could rewind the video and pause it if you want to check it out a little bit more. But the next thing I'd have you do is, this is really great if you got transparencies. If these are all colored on transparencies, because you can stack them. And so we shaded all the multiples 2 through 10. What if we just shaded them all on the same piece of paper? So if you go back to like multiples of 2, if I also did multiples of 3 on the same paper. So you go 3, 6 is already shaded, 9, 12 is already shaded, 15, and so forth. And then we shaded in all the multiples of 4, and 5, and 6, and 7, 8, and 9, and 10. If we went through and did that, and then we erased the first one. So we erased 2, 3, 5. So let me show you. Let me go to where I've got that set up. It would look something like this. So I'm not including 2, 3, 5, and 7 there as far as our first multiples, and I'm not including 1, and that's for a reason I'll discuss in a moment. But notice everything else beyond that first line is I've shaded in multiples of 2 through 10 down below. But some are not shaded. Even though I went through all that, 37 is not a multiple of 2, 3, 5, or 7, or 6, 4. Actually, it's none of these. It's a multiple of. And so the ones that are not shaded here, we start to get the idea of what a prime number is. So prime number, all these unshaded ones are prime numbers less than 100. Now I unmarked 7, 5, 3, and 2 as well there because they don't have anything else that's a multiple. They're not a multiple of anything else but themselves in 1 as well. 4, you say, well, you said you shaded multiples of 4, but notice 4 is a multiple of 2, so that's why I shaded 4. Same with 6 and 8 and 10, and of course 9 is a multiple of 3. So 7, 5, 3, and 2 are not multiples of any of those other numbers, and same thing with anything else that is not shaded down below. So that's where the whole thought of a prime number comes from. I can't make 47 for any other way other than multiplying 47 and 1. 48, though, I could do 2 and 24, 6 and 8. There's 3 will go into it. There's lots of ways I can make 48. Only one way I can make 47, and that's 1 and 47. So that brings us to our definition of what a prime number is. And so a prime number has only 2 factors, 1 and itself. And so a couple of things here. It has to have 2 factors, 2 unique factors. That's important because if we go back to our chart here, notice 1 is not a prime number. I shaded it just because I want to shade something else besides orange just to say, hey, there's something important about 1, and it is not a prime number, but it's also not what we call a composite number. So you say, well, what other factors are there of 1? Well, we're saying that it has to have 2 factors, 2 unique factors. And so the only way to make 1 is 1 times 1. And these are not unique factors. It's the same number. And so it doesn't have 2 factors. Its only factor is 1 there. So therefore, it's not prime. A composite number has more than 2 factors. So going back to this hundreds chart, everything that is shaded in orange is a composite number. You can make 57 by multiplying 3 and 19. You can also make 57 by 1 and 57. So it has more than 2 factors. And so that's why 1 is also not a composite number, because it does not have more than 2 factors. So we say the number 1 is neither prime nor composite. Now, a long time ago, they used to consider it prime, but since then they have removed 1 from the prime numbers set. So when we talk about moving on here, prime factorization, we're going to take numbers that are composite numbers and do what we call the prime factorization of it. And that prime factorization will help us come up with a lot of other interesting things about numbers that we wouldn't otherwise be able to tell. So first thing is, what do we mean by factorization? When we say numbers have factors, we say what are 2 numbers that can multiply to give you that number. So for instance, the number 6 can be made by multiplying 2 times 3. So we say we can factor 6 into 2 numbers 2 times 3. The number 24 can be factored into 3 times 8. So 3 and 8 are factors of 24 because they will divide into 24. You could also say that 24 is 3 times 4 times 2. And so 3 times 4 times 2, all of these are factors of 24. But this is not what we're calling prime factorization, and the reason why is not all of these numbers are prime. So when we say prime factorization, we want to take a number down into just factors that are prime. So if I want to continue this, I could say, wait a minute, 4 can be broken up into, let's move this 30 out of my way for right now, but 4 can be broken up into 3 times 2 times 2, and then that one more 2 right there. So now notice 2 times 2 is 4, and then the 4 times 2 is 8, and 3 times 4 is 24. These are all factors of 24, and they're all prime numbers. So we say that this is the prime factorization of 24. Another way we can write these prime factorizations when you have more than one number that's being multiplied in here is to use exponents. And that's what we typically do. So 2 times 2 times 2 is the same thing as 2 cubed. So the prime factorization of 24 can be written as 3 times 2 cubed. So didn't mean to do that example. Sometimes when I planned on just these three numbers, but sometimes when a number pops in my head or just a thought, it's just easier for me to just go with whatever I'm thinking. So let's try these three numbers out right here. I'll do this one right here, the number 12, and then I'll let you try to work out some of the others. So 12 will break down into 6 times 2, and 6 breaks up into 3 times 2. And notice these three numbers here, 3 times 2 times 2, are all prime numbers. So that's the prime factorization, but let's write it out in exponent form. So it's going to be 3 times 2 2's. So however many numbers you got of this, that's what you're going to write up here in the exponent form. 2 squared means 2 times 2. And so that's your answer for the prime factorization. Now, I always get somebody asks me this question. They say, I didn't use 6 and 2, I used 4 and 3. But the cool thing about this is it doesn't matter. You don't have to see the same thing that I see or someone else sees. So long as 4 times 3 equals 12, you can start from there. And so 4 times 3 is going to break down further into 2 times 2 times 3. And then notice once again we've got 2 2's and 1 3, so we get 3 times 2 squared. Now, one more thought, just in case I don't really ever see it come up. If you say 12 times 1, you could start with that, but it really doesn't get you anywhere. But notice whenever you factor out that 1, you kind of just ignore it, because 1 times anything is the number, and 1's not a prime number, so it doesn't get us anywhere as far as the prime factorization go to use the 1 there. All right, pause the video, try to do 27, see what you get for its prime factorization. All right, so if we start here, I'm going to use 3 and 9, and then 9 breaks up into 3 and 3. So we end up with 3 times 3 times 3. Don't forget about that 3 up there. Sometimes students forget about the number that's hanging up there by itself. It's 3 times 3 times 3, or we can say that is 3 cubed. And then 30, I'm going to say 3 and 10. 10 breaks up into 2 and 5. And 5 times 2 times 3 does equal 30, and those are all prime numbers. So I'm just going to write out like this: 2 times 3 times 5. That's your prime factorization. Cool thing is, if you're unsure if you got the answer right, all you got to do is this. Your check is, are all the numbers prime? And then multiply them out, So if I multiply it out, I should get 30. 2 times 3 is 6. 6 times 5 is 30. Over here on the left, do the exponents first. We do order of operations. So 2 times 2 is, or 2 squared is 4. 4 times 3 is 12. That's what I started with, and they're all prime. Okay. So once you get in the habit, don't leave it as 3 times 2 times 2. Get in the habit of writing in exponent form, just so we work on our exponents, and also it's going to help us figure out a few other things you'll see in a moment. All right, and this is where it's going to start to work. How to find the number of factors. So sometimes I might just say, list all the factors of 24, or another way to say is, what are different numbers that will divide into 24? Like, will 2 go into 24? Yeah, 2 will go into 24 12 times, so 2 is a factor. Will 6 go into 24? Yeah, it will. It'll go in there 4 times, so 6 is a factor. So sometimes I don't want the prime factorization. I just want to know, will a number go into it? And sometimes I want to know how many numbers will go into it. So that's what I'm asking here, is how many numbers will go into 24? Will 7 go into 24? No, it won't. But how should I put it? You don't want to check every single number less than 24, because that can be annoying. Now, 24 is a simple number because it's smaller. You've probably memorized your multiplication table, and you could come up with the answer. But if I gave you a number like 2,432 and asked for the number of factors there, that's going to be a little bit harder to do and time consuming if you're guessing and checking. So there is a method that we can quickly figure out how many factors a number has. So in order to do that, we are going to find the prime factorization. We'll start with 24. Find the prime factorization of 24. So we've got 3 and 8, 2 and 4, and then 2 and 2. And write it in exponent form. So writing this in exponent form, I get 3 times 2 cubed. Now, recall back and say, what is the exponent right here with the 3? And so the exponent there is 3 to the first. Remember, any number raised to the first power is just that base. And any number raised to the 0 power is 1. And we'll talk about this when we get into algebra of why that works, because I feel like that's important for you to be able to explain, like, why is x to the first x and why is x to the 0 1, or 3 to the first 3 and why is 3 to the 0 1. We'll talk about that when we start talking about exponents and algebra. But for right now, just try to recall that from your high school days. And then so if a number is written like this and it doesn't have an exponent written, remember it's just like saying it to the first power. So now that I've got the prime factorization written in exponent form, the only trick we do here to figure out the number of factors is to look at these exponents and add 1 to each one. So if I add 1 to 1, I get 2. If I add 1 to 3, I get 4. And then I want you to multiply that result together. So 2 times 4 is 8. So what this number tells me is 24 has 8 factors to it. So let's check. It's a smaller number. We can check. We've got 1, 2 will go into it how many times? 12 times. 3 will go into it 8 times. 4 will go into it 6 times. And 5 won't go into it, so we stop there. Notice 1, 2, 3, 4, 5, 6, 7. We're missing one. Oh, 24, right? So it's always good to kind of pair them up so you don't forget one. But notice how if it were a quiz and I was taking this as a student and the teacher asked me how many factors or list all the factors of 24, if I didn't know it had 8 factors, I might have accidentally forgot 24 itself was a factor just because I'm thinking in my head and writing it aloud while I talk. So it's a nice check as well. But when you get into larger numbers, if I just ask you the question, how many factors does it have? You can tell me how many factors it has without actually having to figure them all out. So pause the video, try it with 36. How many factors can you come up with for 36? So for 36, we're going to do the same thing. We're not going to list out the factors this time. All we're going to do is say how many factors do we get. So I'm approaching this as 6 times 6, and then 2 times 3, and 2 times 3. So the prime factorization is 2 squared times 3 squared. I'm going to take a look at the exponents and add 1 to each one, and then multiply. So 3 times 3 is 9. So 36 should have 9 factors. So you know what, let's test that out because that seems odd to have an odd number of factors there. So I've got 1 and 36. I've got 2 and 18. I've got 3 and 12. I've got 4 and 9. And then let's see, 5 won't work. Oh, but 6 will work, won't it? Because you got 6 times 6. So you don't count 6 twice because this is a perfect square. 6 times 6, it's not unique to say 6 and 6, so you just got 1 6 in there. So that's why we get an odd number there, because it is a perfect square. So you can pause the video if you want and go ahead and do 33. For 33, if we do the prime factorization, we're going to get 3 and 11, and those are prime numbers. So we're done there, but remember it's 3 to the first times 11 to the first. So we want to know the number of factors. We're going to add 1 to each exponent and get 2 times 2, which is 4 factors. So if I asked you to list the factors, you would say we've got 1 and 33, and then we got 3 and 11. That's a total of 4 factors there. Notice, does this work with prime numbers? So what if we had the number 7? 7's a prime number. List the factors of it. Well, you've got 1 and 7. This is not a prime factorization, though, because 1 is not a prime number. So really, I only have 7 to the first here in my prime factorization. It's already factored to its prime factorization. You could say it like that. It's just 7 to the first. So if we add 1 to that exponent, we get a 2, and there's nothing else to multiply it by. There are 2 factors to 7, 1 and 7. So it works for prime numbers as well. It's just you got to think about it in a different way. Prime numbers are already at their prime factorization. If I give you a large number, I'm probably just going to want the number of factors, not for you to list them. It'll be in any directions, whether it be homework or quiz, whether I want the factors listed. Just make sure you're paying attention to the directions. So let's say we had a number like 300, and I asked you to write out the or how many factors are there to 300. I'm not going to ask you to list the factors. I just want to know how many. So once again, you're going to do the prime factorization. 3 times 100, 10 times 10, and then we get 2 times 5 and 2 times 5. So in exponent form, we're going to say it's 2 squared times 3 to the first times 5 squared. And so this is the prime factorization. I could ask you for that. Or I could ask you to list the number of factors. So add 1 to each exponent. You get 3 times 2 times 3. And this gives me 18. So there are 18 factors to 300. You know, think about it. You got 1 and 300, 2 and 150, 3 and 100, and so forth. But I'm not going to make you list out all 18 factors. If I make you list the factors, it'll be smaller 2-digit numbers. So looking about greatest common factors, what do we mean about greatest common factors? It's the largest number that will go into 2 numbers. So for instance, if we have the number 8, let me switch over to my pen here. If we have the number 8 and 12, what is the largest number that will divide into both of them? Like both can be divided by 2, both can be divided by 1, but 4 is going to be the largest number that will go into both of them, divide into both of them. Now, we know that because they're small numbers and we work with those numbers a lot. It's not always easy to tell when the numbers get larger. So we're going to start with these two, and I'll show you the method we'll use for larger numbers. So the first thing I want you to do is find the prime factorization of both 8 and 12. So if we break down 8, we get 4, 2, and then 2, 2. So 8 breaks down into 2 cubed. And then we break down 12. We get 2 times 6, 2 times 3. So 12 breaks down to 2 squared times 3. So here's the method, and we'll look at some ways we can explain why the method works. Find their common bases. So remember, this is the exponent in this number, this is the base. They both have a common base, or a number with a common base 2. So we're going to write out 2, and then take the smallest exponent between those two bases. So in this case, it's going to be 2 because it's smaller than the 3. 3 is not shared by both, so we're not going to just kind of ignore the 3, and then multiply whatever you got out over here. So 2 squared is 4, and so our GCF, or our greatest common factor here, is 4. Now, let's try a little bit of a larger number than just these two. Let's go with, let's say, let's do 16 and 38. Let's find the GCF between those two. So breaking 16 down, we've got 4 and 4, and then 2, 2, 2, and 2. So this becomes 2 to the 4th. Whoops, 2 to the 4th. This one we just have 2 and 19. And so this is going to be 2 to the 1st times 19 to the 1st. What's the common base? The common base is 2, and take the lowest exponent to it, so 2 to the 1st, or 2. 2 is the largest number that will go into both 16 and 38. Let's try another one. This time I've got 36 and 72. Notice the notation here. I wrote it out as GCF and in parentheses 36 and 72. And so for this, once again, pause the video, find the prime factorization. There we go. I paused it so I'd save you a little bit of time. This broke down into 2 and 36, and then 36 has the same factorization as this 36 over here. And so now as I do this, this is 2 squared times 3 squared, and this is 1, 2, 3 2's, 2 cubed times 3 squared right here. So for this one, we've got more than one base that are in common, so we're going to be writing out two bases. So the first base in common is a 2, and I'm going to take the lower of the exponents, 2 squared, and then the next base is 3, and they both have a 2 up top, so I'm going to leave it like that. And then I'm going to multiply everything out. So 2 squared is 4, and 3 squared is 9. 4 times 9 is 36. And that should make sense. We know 36 will go into it once here, and 36 times 2 gives me 72 over there. Now the reason why this works is we can kind of show this with a Venn diagram. So let's set that up. This is not quite as even as I wanted it, but if I'm listing in these bubbles the factors of 36 and the factors of 72, if I wrote this back out to my factorization right here before I put it in exponent form, I could say, okay, they both share a 2, so they overlap in 2 right there. I can cross a 2 off. They share another 2, cross those off. They don't share that third 2. That just belongs to 72, so I'm going to write the 2 out here. They share a 3, and they share another 3. So I end up with 2 times 3 times 2 times 3, and what they share right here in the middle is 36. So this is my greatest common factor between the two of them. So that's a great way to illustrate why this method works, not just how to do it. Now, we can also show these using Cuisinart rods. Let's go back to our more simple example of 8 and 12, because otherwise we're going to run out of space on this particular digital manipulative. You could use it in the classroom with like a larger graph paper and more Cuisinart rods, but we're going to look at the GCF of 8 and 12. So if I write out 8 right here, and for 12 I'm going to use a 10 and a 2 rod here. So there's 12. And all you got to do when you're talking about GCFs between these is pick a number that will go into both of them. And students, this is a great way for students to see multiples, is have them physically move these things and say, okay, 2 will go into 8 because I just did that. Is there a bigger number that will go into 8? So if they try out 3, for instance, they don't really know their multiplication table yet. If they try out 3, they notice that 3 will not go into 8 evenly. So 3 does not divide 8. So even though it might work for dividing out over 12 over here, it doesn't work for the 8. 4 works. Will 4 go into 12? And they can see, hey, that matches up. So 4 will divide into both of them. Will 8 go into 12? They can look at it that way too. We know that 8 goes into 8, but 8 will not go into 12. So they see that their GCF here is 4. And you could use it for larger numbers, just digitally though, it's not going to work unless you're got smaller numbers. All right, so that's using Cuisinart rods, that's using the prime factorization method. You can also do it for larger numbers, not larger numbers, more numbers. So let's suppose I asked you for 3 numbers here. Let's try, what's the GCF of 10, 45, and 5. So the GCF, let's not do 5, let's do 55, just so it's a little more interesting than a small number like that. So if we did our prime factorization on each one of these, we'd say this is 2 and 5, this is 5 and 9, which breaks down to 3 and 3, and this is 5 and 11. So looking at these, I say, rewrite this is 3 squared times 5 to the first, 2 to the first times 5 to the first. I'm just putting these in parentheses so you can see them separately. And what base do they have in common? They only got one base in common, and that's 5, and it's to the first power there. So the GCF of all of these is equal to 5. So sometimes you'll see that on your work where you got to do 3 numbers, and you just do it the same way. It's just you want one that has to be present in all 3 of them to find a GCF. All right, the next we're going to look at is a least common multiple. Now, multiple is different than a factor. Remember, we did those hundreds charts, and we said mark out all the multiples of 3. So you're marking out 3, 6, 9, 12. It's what I'm multiplying. I'm multiplying 3 by a whole number to get another number. So anything that divides into 3, or 3 divides into, is a multiple of 3. So in this case, I wanted to find out what is the least common multiple. What's a number that they both will go into evenly versus a number that will go into both of them evenly. So for this one, we're going to look at, this time, the least common multiple of 8 and 12. So don't get it confused with greatest common factor. That was 4, because 4 will go into both 8 and 12. Now I want a number, the smallest number that I can make, that both 8 and 12 will go into or divide into. So once again, break this down into its prime factorization. So we get 4, 2, and then 2 times 2. So it's 2 cubed. And this one is 3 and 4, 2 and 2. So we end up with 2 squared times 3 to the first. So last time we just said find the common base and take the smaller exponent. So we ended up with 2 squared, which is 4, because that was the GCF. This time I want, for LCM, every base represented. So we've got a 2 and we've got a 3. And then take the highest exponent and put that in. So we want 3 and we want a 1 right there. And then multiply everything out. So 2 cubed is going to give us 8. 3 to the first is 3. And 8 times 3 is 24. Now in this case, you could go through and say 8 plus 8 is 16. 12 won't go into 16. 8 plus 8 plus 8 is 24. 12 goes into 24. That's the smallest number. But when we get into larger numbers, it becomes harder to do. So just to kind of restate that, we find the prime factorization. Each base has to be pulled out and take the largest exponent and let it be represented with the largest exponent. Now, if we look at this with the Venn diagram, it's a little bit easier, I think. So let's check it out with the Venn diagram. And so we've got 8 and we've got 12. Here's our prime factorization. And the 2, so we've got 2 times 2 times 2 and 3 times 4, no, sorry, 2 times 2 here. They both share a 2. They both share another 2. This 2 is not shared over here, so it goes on the outside. So notice in this bubble, 2 times 2 times 2 is 8. This 3 is not shared on both, so it goes over here. So in this bubble, 2 times 2 times 3 is 12. And so once again, if we're looking for GCF, the GCF is found by multiplying this football shape here. 2 times 2 is 4. GCF is 4. If I'm looking for the least common multiple, though, all I have to do is multiply all the numbers I see in the bubble. So 2 times 2 times 2 is 8, and then 8 times 3 is 24. So our LCM is the product of all the numbers in that, 24. Now be careful here. It's not the same thing as multiplying 8 times 12. 8 times 12 is 96. So what happened there? Remember, you took out a factor of 4 because they share a factor of 4 in here when you only wrote down 2 once and marked off 2 2's. So let's do another one because I feel like that's always helpful to see a second example. So let me clear this. And let's find the LCM of, let's do 18 and 27. So a little bit larger numbers there that won't be as obvious to work with. So pause the video and the first step, find the prime factorization. All right, so I did the prime factorization there. I got 3 squared times 2 to the first, and then 3 cubed on for the 27. Remember, to find the LCM, I'm going to take each base and write it down, 3 and 2. And then I'm going to take the largest exponent between the two. So 3 squared and 3 cubed. I'm going to write down 3 cubed. 2 to the first, and no 2 over here, so I'm going to write 2 to the first. 3 cubed is 27. 2 to the first is 2. Multiply them, you get 54. If you want to show it on the Venn diagram, if you like that method, then do that method. So to do the Venn diagram method, I'm going to just take a step back and forget about the exponential look here and look at 18 as 3 times 3 times 2 and 27 as 3 times 3 times 3. So I've got 3 shared by both, 1, 3 there, so I'm going to write it down in the middle. Here we'll do 18 and 27. Another 3 shared, so I'm going to write that down in the middle. There's a 2 right there. It's not shared, so just write it on the outside. And then there's a 3 that's not shared between the two. I'm going to write it right here. So in this bubble, I got 3 times 3 times 3, which is 27. And this bubble, I got 2 times 3 times 3, which is 18. If I had asked you for the GCF, you could say it's 9, because inside the football shape multiplied is the GCF. But if I want the LCM, it's going to be all these numbers multiplied. So 3 times 3 times 3 times 2, and you'll get 54 for the LCM. So we can just say equals 54. And you can show your work by doing the factorization and then doing the Venn diagram, or you can do the factorization and use the rules there for the exponents. One other way we can use it is with Cuisenaire rods. 18 and 27 are pretty large numbers used for Cuisenaire rods, so we'll go back to our example of 8 and 12 and show that with Cuisenaire rods. And so for a student that likes Cuisenaire rods, or a teacher that wants to show it that way, we can just start writing out 8 and 12. Remember, our 12 is made up of 10 and 2. Or you could do 6 and 6 if you wanted to. Let's do that. That seems like fun. So there's 112, and you can put an 8 with it and show, well, they're not the same. And then you just match these roads, keep building these roads until they match up. So another 6 and 6 go right here. And then another 8 would match up with it right there just before we run off the page. So that's good. So now we can count these individual blocks, or you could just multiply 3 times 8, 4 times 6, and it shows that their LCM there is 24. Okay. Try out the homework. Let me know what you think. Let me know if there's any, if you have any questions. One more thing, I almost forgot. With LCM, we can also use 3 numbers and do the same method there. So I could ask you, what's the LCM of 6, 8, and 12 if I wanted to. And in that case, you would have 24 there as well. But anyway, same method, just adding one more number in there that they all have to have in common. Anyway, do the homework. Let me know if you have any questions, and I'll be happy to answer those. Thanks for watching this video, and I hope you're having a great day.